Do you know what is this computational graph used by deep learning frameworks like TensorFlow or PyTorch? No? Let me tell you then. The whole logic behind how a neural network functions is a backpropagation algorithm. This algorithm allows to update the weights of the network such that it can learn. The key aspect of this algorithm is to make sure we can compute the derivatives or the gradients of very complex functions. That is the whole point of the computational graph. It is to make sure that we can backpropagate those derivatives to the whole networks, how deep it may be. So let me show you how it works. Let's get into it. A big part of deep learning is to find a way to take derivatives of very complex functions or gradients in an efficient manner. Most deep learning frameworks, they use the concept of computational graph. So let's look at a small example to see how we can use this computational graph to compute derivatives. So let's take this example where we have a function of three variables. We have x, y, and z, and the function is f. And it is a very simple function. We take the multiplication of x times y times z. So let's construct a graph where at each node we get some variables, and the way those variables interact with each other is through operations. So for example, I'm going to have this interaction between x and y through the multiplication operation. So now I create another node in the graph where the value is x times y. Then we can construct another node by using the operation multiplication. So we can take the resulting node that was x times y and we can multiply it to z, and we get a new node in this graph that is x times y times z. This is usually called the forward pass. We compute the full function by traversing the graph and arriving to the node that does not have an outgoing edge. So now let's see how we can compute derivative within this graph. So let's say that I want to compute the derivative of the function f with respect to z. If I take this graph and I just compute the derivative with respect to z, I know that I just need to remove z from the node that we have here. By removing z, we get x times y. By knowing the rules of derivation for the multiplication operation, I can directly compute the derivative of f with respect to z. And now we're going to store this derivative in the node z. Now let's try to compute the derivative for this node. So we want to compute the derivative of the function f with respect to x times y. So this is the same thing when it comes to the multiplication operation. To take the derivative with respect to a specific variable, I just need to remove this variable when we have a simple product. So we have here a simple product of this variable x times y times z, and to take the derivative with respect to x times y, we just need to remove it, and we end up with z. And now we can store this derivative at the node x times y. Now let's look at the derivative of f with respect to x. To find the derivative, we can apply the chain rule, and the computational graph will help us understand how to apply those chain rules. The derivative of f with respect of x is equal to the derivative of f with respect to x times y times the derivative of x times y with respect of x. I already computed the derivative of f with respect to x times y, so I can pull it from this node. So now I just need to compute this derivative. Because this is a simple product, I just know that I just need to remove x to get the actual derivative. So this will give me y. So we end up with z, because this was the derivative of f with respect of x times y, times y, because y is the result of the derivative of x times y with respect of x. And now I can store it into x. So you see that I don't need to know what f was to actually compute the derivative of f with respect to x. I just need to follow the computational graph to take the previous value that was computed in the graph. I can do the same thing with y. If I want to compute the derivative of f with respect to y, I know that this is the derivative of f with respect of x times y times the derivative of x times y with respect of y. I already computed the derivative of f with respect to x times y, so I can put it here. And the derivative of a simple product will result of just removing the variable y to get x. And now I can store the resulting derivative into the y node. So this was a backward pass. I computed the function first in the forward pass, where I was able to capture the whole computational graph, and by applying the chain rules, I was able to backpropagate the gradients for each of the nodes of the computational graph. You understand that this computational graph could be extremely complex. I could have thousands, billions of nodes. As long as I know the derivative of the unit operations like multiplication, additions, even exponential or log, I can always backpropagate the gradients to the beginning of the graph. So in principle, as long as the function is analytical, I'm able to compute the gradient for any function that could be stored into a computational graph. And this could be an extremely complex function, but I could always compute the gradient of it in a very efficient manner, store the different gradients, and capture those values very quickly. So let's look at this example in PyTorch. So I'm going to import PyTorch, so import torch, and I'm going to create a very simple tensor, and it's going to have the value 2. I'm going to say that I require the grads, the gradients, to be computed. So these gradients are going to be stored into the computational graph. I'm going to create another tensor. This is just going to store the value 3, and another tensor that will store the value 4. All those variables, I require the gradients to be stored into the computational graph. So let's create the function f. The function f is just the product of x, y, and z, like we just did. And now we're going to compute the gradients. In PyTorch, to compute the gradients, I just need to apply the function backward. So backward is going to backpropagate the gradients up to the initial nodes in the graph. And now we can look at the different gradients that have been computed. So I remind you that the derivative of f with respect to x is y times z. The derivative of f with respect to y is x times z. And the derivative of f with respect to z is x times y. So we're going to print the gradients of x. So this is going to be this. So let's make sure we understand what it should be. So because the gradient should be y times z is equal to 3 times 4, which is 12. Again, I'm going to print the gradients that are stored at y. It should be x times z, and x times z is 2 times 4. I'm going to print the gradients that are stored at the z node. Because the derivative of f with respect to z is equal to x times y, I should have that the derivative is equal to 2 times 3, which is going to be 6. So let's print that, and we get the results. So 3 times 4 equals 12, that is good. 2 times 4 equals 8, this is good. And we have 2 times 3 equals 6. So everything worked according to plan. So let's look at an example where the computational graph is much more complicated. So let's assume that we have an input x, and we pass this input x through a computational block. I'm going to call this computational block h of x. So h is like a function, and the computational block can be many different computations that utilize operations that I can compute a derivative of. And then out of this computational block, I get a result that would be an output y. So x can be a tensor, y can be a tensor. It does not really matter. They are just input and outputs. So now let's imagine that I have another computational block, and this computational block, I'm going to call it f of y. So it takes a variable y, and it generates an output z. And those computational blocks can be very complex computational blocks. When we think about neural network, you could imagine that those could be some transformers or could be some convolutional networks, etc. It can be anything that is typically used in a neural network. So this is a forward pass. I go from the input to the output through the computational block, and I compute the output little by little. So now let's imagine that I want to compute the gradient of z with respect of y. This character means that this is a gradient of z. The gradient is very similar to the concept of derivative. So I'm going to use this sign to capture the concept of gradient. I can easily do it by doing exactly what we did in the earlier example by backpropagating the gradients up to y, where I can store the gradient of z with respect to y. So this is very similar to this example where I was able to store the different derivative at the initial nodes of the simple computational graph. The fact that the computational graph is more complex does not really matter. I can always compute the gradient of the initial node of the graph. Now let's compute the gradient of the output with respect to the input x. So to do that, I can just apply the chain rule. So the gradient of z with respect to x is equal to the gradient of y with respect to x times the gradient of z with respect to y. I already computed the gradient of z with respect to y, so I can take it from here, and I just need to compute the gradient of y, which is the output of this computational block, with respect to x. Because again, I can backpropagate the gradients through this computational block, I can compute the gradient of y with respect to x. And now I'm going to store into x the gradient of z with respect to x. And this was a backward pass. Again, this is exactly what we did with a simpler example. So again, let's look at a simple example in PyTorch. So I'm going to define a first function, h of x, and this is going to return x squared. I don't really care, I just use a very simple function, and this is going to be good to showcase the example. Now I'm going to define another function, the function f of y, and it's going to return y plus 1. Now let's define a tensor. So I'm going to define the tensor x. This is going to simply be 2 wrapped into a tensor function of PyTorch. I require the gradients to be computed, and I'm going to define the computational blocks. I'm going to have x that goes through h, so it's going to generate y, and I'm going to have y that goes through f, and is going to generate z. So this is exactly the same network that we just looked at, but this is in a simple PyTorch code. Now let's compute the gradients. I just call the backward function. This is going to backpropagate all the gradients for all the different nodes in the network. And now I'm going to print the gradient that will be captured at x. So the gradient captured at x is the gradient of the output with respect to the input of this network. So this is going to be the gradient of z with respect of x. So let's print this. And we have 4. Let's see if this is right. So the whole function is actually x squared plus 1. So this is equal to z. So if I take the derivative of z with respect to x, the 1 goes away, and I get 2 times x. X is equal to 2, so 2 times 2 is equal to 4. So this is right. So I can have as many computational blocks as I want. So let's imagine we have input x, and we're going to pass it through a first computational block, and this is going to create an output x1. I'm going to have another computational block, and it's going to create an output x2. And I'm going to iterate this with as many computational blocks as I want. In the end, I'm going to get an output that I'm going to call xn. And I will have a final computational block, and this will generate a final output z. And I'm going to refer to this as the forward pass. So little by little, I pass the inputs through the different computational blocks, and I generate the output. And I do exactly the same thing. Now I want to create the gradient of z with respect to x of n. And I can simply backpropagate the gradients through the computational block. And I can store the gradient of z with respect to x of n. So you understand that I can iterate this process through all the computational blocks. So imagine that I already computed the gradients that should be stored at x2, and I want to compute the gradient that should be stored at x1. Again, I'm going to apply the chain rule. So the gradient of z with respect to x1 is equal to the gradient of x2 with respect to x1 times the gradient of z with respect to x2. The gradient of z with respect to x2 is already computed, so I don't need to compute it anymore. I can just pull it from the previous node. And the gradient of x2 with respect to x1, I can simply compute it by backpropagating the gradients through the computational graph of this computational block. And I can, like we did before, compute this simple gradient. Now, this gradient ends up to be a simple product, and I can store this gradient in the node x1. Again, to compute the gradient at the x node, I'm just going to apply the chain rule. So if I want to compute the gradient of z with respect to x, this is equal to the gradient of x1 with respect to x times the gradient of z with respect to x1. The gradient of z with respect to x1 is already computed. I just need to compute the gradient of x1 with respect to x, and I can simply compute this gradient by backpropagating the gradients through this computational block. And I can finally store the gradient at this node x. And this is a backward pass. I was able to compute the gradient of the output with respect to the input by iteratively applying the chain rule and capturing the different gradients at the different nodes of the computational graph.